by Weiqing Han from the Department of Atmospheric and Oceanic Sciences from the University of Colorado in the United States. Thank you very much, Weiqing, for joining us tonight. She's connecting via remote. This is a consequence, as you can imagine, of the pandemic and the restriction of travel with the United States, which are particularly difficult also in respect to the travel from the United States to Switzerland. It has now recently changed, but before it was really difficult to come here. Therefore, we have this talk today in the form of a Zoom talk. We hope that next time in March, then we will have our first normal talk again. But as you know, this is currently difficult, very difficult to predict what will be the further development of the pandemic. But in any case, I would like to introduce to you our speaker of today. So Weiqing Han obtained her bachelor degrees from Nanjing Institute of Meteorology. She then obtained her master's degree from the Chinese Academy of Sciences in Beijing. She then moved to the United States to obtain her PhD on physical oceanography from the Nova University in United States. She then worked as a postdoctoral fellow at ATOC, so in Colorado, at the Department of Atmospheric and Oceanic Sciences. She there became in 2002 an assistant professor, then an associate professor, and since 2016, she's a full professor at the Institute. She's a member of numerous different associations, like the American Association for the Advancement of Science, the American Geophysical Union, the Meteorological Society, and the Oceanography Society. And she has had many honors, including a fellowship from the Excellence Cluster in the University of Hamburg, Germany, and most recently in 2002, she was selected as a Johannes Geiss Fellow at ICI. So we thank you very, very much for joining us today and giving this talk. Please, Weiqing, you have the floor.
Thanks, Christoph, for the introduction. I'd also like to thank ISSI for providing the opportunity to give this talk. So today I'll share some of my research in the Indian Ocean on the planet Earth and change the ocean circulation, sea level, heat content, and their impact. So this is the trend for the observed sea surface temperature in 115 years from 1901 to 2015. So the positive values here shows the warming trend, like the ocean is warming, and the negative values, like blue, shows cooling. Okay. Due to the increased concentration of greenhouse gases in the Earth's atmosphere, which traps heat to the Earth's climate system, and this amount of heat, over 94%, enter the ocean. Therefore, the ocean has been warming. So the time series of this sea surface temperature anomalies averaged in the global scale also shows a increasing like a warming trend here. Okay, based on this 30-year average from 1971 to 2000. Okay, due to this warming and due to thermal expansion and also melting land ice, the global sea level has been also increasing in the past century. Okay, so this warming and sea level rise, however, is not geographically uniform, as we can see from this SST sea surface temperature trend, and there are stronger warming in most part of the Indian Ocean, accompanied by a weaker warming in the south tropical Indian Ocean basin. Compared to the vast basin size of the Pacific and Atlantic Ocean, the Indian Ocean is small. Okay, despite its small size, the Indian Ocean rim is home to 1/3 of the world populations. And more importantly, most of them live in developing countries with low-lying coastal areas here, as we can see, India, Bangladesh, Myanmar, here, Indonesia, this side, Somalia, and the African coast. So they are highly vulnerable to climate variability and climate change, so such as global and regional sea level rise. Okay, so here in this talk, I first discuss this spatially uneven sea level rise patterns over the Indian Ocean since the 1960s under the greenhouse gas warming. So this understanding is important because it could help inform resource allocation, because if we have a limited resource, we can't allocate everywhere, but some very highly vulnerable places should be allocated. Okay, adaptation and response options for human society. Then I'll discuss a little bit the impact of this global sea level rise here on the extreme sea level events along the Indonesian coast in recent decade. And we know that the Indonesian islands have been subject to strong sinking, and Jakarta, their capital city, sinks the fastest among the cities in the world. Okay. Plus large amplitude extreme sea level events and the global sea level rise increased vulnerability of Indonesia. Lastly, I will discuss a little bit about this upward trend, like regional sea level trend interaction with the natural internal variability on decadal timescale. So the rapid increase of ocean heat content in the Southeast Indian Ocean off the Australian coast here during the recent global surface warming hiatus, like surface warming almost stopped that period of time, and this warming impact on the marine ecosystem. Okay, since this study, since here, the rest of my talk will mention something about the modeling, like climate modeling and the ocean modeling. Here, I'll briefly introduce these climate models, okay? And here, this is this picture shows this real Earth's climate system. We have different components. We have atmosphere, we have hydrosphere, okay, lithosphere, and biosphere. Climate models actually mimic this realistic Earth's climate system. We have atmospheric model component, ocean model component, land surface model, and sea ice model. Some models also include this land ice, like ice sheet, okay? And these different models, each of them a set of equations, okay? And this set, all different components interact each other, which resembles a real Earth's climate system that with different components interact with each other, okay? So using these model simulations, we can assess the impact of external forces, such as greenhouse gas warming. Okay, we will see part of those, okay? And we distinguish them from natural internal climate variability. What does that mean? That means that even we don't have external forces, such as the sun, see here, assume we fix the solar energy come to the Earth's climate system to a just mean climatological seasonal cycle, and do not allow it vary from year to year and longer time scale. And also we do not have volcanoes and no fixed constant greenhouse gas concentration. The interaction between all different components still produce variability. And those variability are natural internal climate variability. That's what we see, like this year is La Nina year, right? That's part of ENSO, that's a negative phase of ENSO, that's a natural internal climate variability, different from the greenhouse gas forced variability, okay? And when I mentioned the ocean model simulation, and this, I just take the ocean model component and forced by the observed atmospheric wind and freshwater flux and heat flux. Okay. All right, first, so let's see the uneven sea level rise patterns. So this is the model, ocean model simulated the sea level anomaly, and for a 50-year trend. This is the trend, okay, from 1961 to 2008, close to 50 years. Apparently, and we see a distinct spatial pattern with the sea level rise along Indian coast, Bangladesh, Myanmar coast, and this Indonesian coast, Australia, Madagascar here, almost everywhere, except for this southwest tropical Indian Ocean seashores area, okay? And as we know here there is a sea level falling trend, okay? All right, so we know this is the model simulations. How about observations? We do not have such a long observations and for the basin-wide scale available everywhere, okay? And based on that, I'll show here, but we have tide gauge observations along the coastal areas and the island region. Here, I choose this tide gauge data that has the length 20 years and longer. So here, around here, the black line shows time series of the tide gauge observations at each of the 10 locations here around the Indian Ocean coast, as you can see. And this blue line shows the model simulated sea level anomaly. Apparently, both the tide gauge observed and the model simulated sea level shows a rising trend almost at everywhere along this Indian Ocean coast, okay, everywhere except for Zanzibar here, okay, and the sea level has a downward, like falling trend, which agrees with the model simulations pattern. All right, so this distinct spatial pattern of the sea level is not that sensitive to the time period we choose, as long as it's pretty long, like 40 to 50 years long. So this is from 61 to 2008, but here from 61 to 2001. And here, this one is we use ocean ORAS4, that's ECMWF. It's the ocean reanalysis data. Reanalysis data means that ocean model, but assimilated observed data, okay? So sometimes people use this as observations, okay? But these model simulation I show on the left are just the model, there's no data simulation, just forced by atmospheric wind and the fresh water and heat fluxes. See here, as we see, these patterns really exist also in the reanalysis data, okay? And also the time series of these sea level anomalies in all the four representative regions, as we see, shows clear this rising trend, of course, in these three areas, and the falling trend in this southwest tropical Indian Ocean over seashores area. And more importantly, here, the model simulated sea level anomaly agrees so well with satellite observed sea surface height anomaly, which only exists from October 1992. That's topics starting. So here, look, for all those regions, the same model simulated sea level anomaly agrees with satellite observations. So all of these indicate that this sea level spatial pattern, okay, is robust, right? And the rising trend around the Indian coast, Bangladesh, and also Indonesia, and of course here Australia and Madagascar, this really exert this threat or increase vulnerability to these third world developing countries, okay? All right, so if we remove the global mean, we can identify in which area that the sea level rise is faster than the global mean, and which area the sea level rise is much slower than the global mean. So this one we from this ORE-S4, the ECMWF reanalysis data remove global mean. Apparently, along the east coast of India, Bangladesh, Myanmar, and Indonesia, all the coast, this sea level rise is much faster than the global average sea level rise. Okay. All right, so here I just got searched this from the website, and this is from a newspaper. It's saying that this is from March 16, 2021, this year. Okay, this is news. And the city in Java, which is right here, the city in Java could disappear in 15 years due to land subsidence and coastal flooding. So, and here we show that there is a multi-decadal trend of sea level also rising here, showing that the sea level rises much faster than the global mean along this Indonesian coast. All right, to understand why there is such a pattern in the multi-decadal sea level trend. So here we did a model experiment, but here it only shows this surface wind pattern. And those arrows here, okay, shows the surface wind trend, okay, for the same period of time as this sea level trend here. So in the ocean, briefly, I won't go to details, but one thing I wish to introduce is that for we call the westerly wind, the wind blow from west to the east in the ocean, it causes not only eastward current along the equator, but also this ocean mass, like surface water converge to the equator, so like this. Because when the wind blows from west to east, because the Earth's rotation and the Coriolis force causes it's in the 90 degree to the right, okay? And in the northern hemisphere, and then 90 degree to the left of the wind direction blowing here, okay? And in southern hemisphere. Therefore, the surface warm water converge to the equator, and then the westerly wind, the wind blow from west to east, also produce eastward current, okay? That carries warm water to the eastern boundary. And when they impinge on the eastern boundary, they, okay, transient signal is coastal cavern waves. But here we just want to, I just want to say that when the mass reach the eastern boundary, they also flow poleward along the coast. Therefore, as we can see here, we produce the high, you accumulate the water, warm water, which is high sea level here, and also spread poleward along the coastal area. So you can see coherent sea level increase along the Indonesian coast. Okay. All right. So for the open ocean here, why does here all of a sudden you get a blue like a sea level fall? Look at the wind pattern clockwise. If we think about this southern hemisphere and Ackermann transport, we call it Ackermann transport, which is ocean, the seawater, surface, warm water transport is in 90 degrees to the left in the to the wind. The wind blow this way, so 90 degrees to the left is here, southwest. And here, 90 degrees to the west is westward. Here is northward, okay? So this means surface mass diverge from this area when you have clockwise wind pattern. So the warm water is removed, cold water comes up from the subsurface. Therefore, thermal contraction, you got a low sea level, okay? So in this area. Therefore, this basin-wide, okay, spatial pattern of sea level rise is driven by the changing surface wind. Then you may ask, why there is a changing surface wind? Here, I won't have time to discuss too much here. I only go through this schematic diagram. So atmospheric circulation in the tropics has zonal circulation, we call the WARC circulation. If we perform this meridional mean, like a 25 degree north, 25 degree north, let's perform the mean. So we get an east-west circulation pattern. So with the warm air go up over this warm surface ocean, warm air goes up in the East Indian Ocean, and the upper level go west and sink down to a relatively cooler sea surface temperature area, and then flow eastward at the surface. Therefore, the westerly wind that blows from west to the east at the surface, okay, is the lower branch of this enhanced Weiqing circulation. And this, we call this wind, this wind produce this clockwise wind pattern. Northern hemisphere is southward. If we perform the zonal mean, you obtain this meridional atmospheric circulation and this northward wind in southern hemisphere. Southward wind in northern hemisphere, like blue arrow, is surface branch of this Hiatus circulation. Therefore, this intensified surface wind pattern that drive this unique or distinct spatial pattern of sea level is represent intensified Weiqing and Hiatus circulations over the Indian Ocean region. Okay, so here, that's what I just said. Okay, surface wind, part of this intensified atmospheric circulation. All right, so to what extent is this pattern of this surface wind result from anthropogenic greenhouse gas warming? And actually, in the early work, and my co-authors and I, we did a series of atmospheric model experiment and forced by different sea surface temperature, showing that this surface wind pattern result partly from anthropogenic warming, maybe other part from natural, as we mentioned earlier, internal climate variability. Then, can the current climate models simulate this greenhouse gas warming? As I mentioned earlier, we can use these climate models, okay, to assess this greenhouse gas warming. So this is a sea level trend from 1958 to 2005. That's from 100-member ensemble average. What does this mean? This means purely represent multi-decadal trend forced primarily by greenhouse gas warming. Of course, there's a volcano stuff, but for over 50-year trend, primarily represent greenhouse gas warming. Okay, this is from Max Planck Institute of Meteorology, 100-member ensemble average, and this one from the National Center for Atmospheric Research here in the US, 40-member ensemble. So these represent sea level spatial patterns forced by greenhouse gas warming. Unfortunately, although both produce some sort of spatial pattern, but they do not agree well. But MPI model shows better agreement with the observed and simulated pattern I showed earlier, with sea level fall over seashells and relative low sea level rise, or slower sea level fall or sea level rise in other parts. But the NCAR-CESM has much larger bias. Okay. So we also analyzed other, like the recent new CMIP5, like IPCC, the 6th assessment climate model result, but they do not agree. Although our state-of-the-art climate models can simulate global greenhouse gas warming on global scale, and also the global sea level rise due to the thermal expansion caused by the anthropogenic warming, but on regional scale, they do not agree. That's you need more work to improve the model. Okay. So although the basin-wide surface wind is the major driver for this distinct spatial pattern throughout the whole Indian Ocean basin, and we know that this Indonesia and Australia sits right between the East Indian Ocean and the Western Pacific Ocean. So here, this is the mean pattern of sea surface temperature, as you see the color, and the white here show cloud, like atmospheric convection ratio. And these shows the Weiqing circulation I mentioned earlier. So this surface here branch from the east to west, we call it easterly trade wind over the Pacific Ocean. Okay, so when we have enhanced the easterly trade wind, it will pile up warm water to the Western Pacific, and therefore it will increase this warm water that flow from the Western Pacific to the Indian Ocean. We call this part the Indonesian Throughflow. Okay, so this figure further shows a more clear picture of the Indonesian Throughflow. On average, the warmer and fresher water flows through here from the Western Pacific into the Indian Ocean through the Indonesian archipelago here, and also strongly affect West Australian coast and the Indonesian coast. So the rest of the talk will focus on the two areas. This area, very vulnerable, and the lack of resources to combat climate change, but meanwhile, the land is sinking fast, okay? On the other hand, the extreme sea level events really have large amplitude in this area. And we also discuss here West Australian coast. Okay, so here I bring up this trend map again here along the Indonesian coast here. All right, we see coherent locals. This is Sumatra and this is Java, and coherent sea level rising trend on multi-decadal time scale. Okay, here and here sea level rise is faster than the global average. Okay. All right, so next I'll look at this time series of sea level anomaly and averaged over southern Sumatra coast, that's blue, and averaged along the Java coast, that's red. All right, and as we can see clearly, this is the upward trend, even we can visually identify. Here we have a sea level rising trend, agree with this sea level trend pattern we discussed earlier. Not only the two Sumatra and Java coast has coherent upward rising trend, but also have coherent sea level variability. And these are based on monthly mean. Okay, we remove the climatological seasonal cycle. This is just change from year to year, from decade to decade. As you can see, these anomalies along these two areas also highly coherent. Okay, we'll discuss later why this is the case. Therefore, and next we'll primarily discuss the Java coast because it has slightly larger variability magnitude in sea level. And here, as we can see, the sea level extreme, okay, high sea level event in 2016 and reached the amplitude 0.45 meters. On monthly mean time scale, half a meter, that's huge. That's very, very high. Okay. All right, to detect this extreme sea level event and to define the extreme sea level event, we use the sea level, we use the satellite observed sea surface height observations, which is the black line, okay? And the tide gauge observations, which is the blue line here at Java coast, tide gauge station, this location at Java coast. Okay, the red line shows sea surface temperature, but here, let's forget about this one. We won't discuss that. Let's focus only on this black line, the satellite observations near. Okay, the nearest location at to this tide gauge, okay, area, which is about 18 kilometers southeast of this tide gauge location. But tide gauge data only have 10 years data, but satellite starting from 1993 here. Okay. So here, this blue line, I show the two standard deviation value, which is 2.6. It's very, very close to the 90th percentile of this satellite data in the past decade, starting from 2010. Okay, so I'll use this to define this extreme sea level event here. So based on this criteria, and we identify 10 extreme events as we mark here, okay? And this 10 extreme sea level event, 9 occurred in an 8-year period, starting from 2010 to 2017. Only 1 occurred in 1998, okay? And here, this second panel I showed is this satellite repeat, this black line, the satellite data. And here, the red one shows again the ORIAS for reanalysis data, which is ocean model assimilated observations. And the blue and the green line shows the purely forward two independent ocean general circulation model forced by observed atmospheric wind. Okay, and all of this agrees so well. Why I'm showing this? Because this reanalysis data and the ocean model simulation, they have a longer period than this satellite data. Okay, so we can put this satellite error in a longer term context. Okay. All right, this third panel, we want to examine what we want to know. Okay, how much the anthropogenic warming, global, we know that anthropogenic warming causes global mean sea level rise, and how much this anthropogenic global sea level rise affect this amplitude of the extreme sea level over the Indonesian area. Okay, so to understand that, what we did is for every single decade, we find the 90th percentile from OI. Let's look at the red solid line here. That's the 90th percentile of the amplitude of this of the sea level anomaly. Okay, and this is for the 1970s and 1980s. As we can see here, oh, this ORIS4 shows persistently increasing the amplitude, but here you do have a down, or a little bit down in the early 2000s, and then you got up, okay? And you have this, okay, the amplitude, the magnitude of the extreme sea level event, yeah, increasing in time in the past several decades, okay? So if I let's remove the anthropogenic global sea level rise from this data, and then do the same 90th percentile, that's the dashed red line, as we see. Okay, and dashed red line, if you look, wow, that's much that dropped by 0.1 meters. What does this mean? Global sea level rise does enhance the extreme sea level by 0.1 meters. Okay. All right, the same thing happened for this ocean model simulation, as we can see, similar situation. To further show this global sea level rise, on this extreme sea level event. And next, I'll show this time series, okay, for this whole period of time, but I only show the period of the satellite error to make the figure more clear, okay? So here we can see this difference between the solid and the red dashed line shows the global sea level rise effect on the extreme sea level magnitude, but this dashed line here, compared with dashed line in 1960s, shows the internal decadal climate variability impact, also increased the magnitude of sea level here, sea level extreme. Okay, so this is a time series. Of course, this is a total from the ROMS, like the ocean general circulation model simulation. That's black line, as we showed earlier, agree well with satellite observations. All right, and this red shows this anthropogenic global sea level, right? And this blue shows natural, we call it internal decadal climate variability. It's not forced by greenhouse gases or anything, okay? And apparently this blue line is the same as the black, but with these two, with anthropogenic global sea level rise and natural decadal variability removed. So if we compare the black and the blue line, we see that, okay, without excluding global sea level rise and decadal variability, this extreme sea level does not have the preference like after this 8-year period anymore, as you can see. Okay, it does not have the preference anymore. It's spread everywhere. Okay, this event. Okay, so for a longer period of time, okay, so along Java coast, this is from reanalysis, or as for reanalysis data, the same thing. Okay, if we remove the global sea level rise and decadal variability, look at the blue, and the extreme events, that's not just concentrate on this 8-year period of time, rather it's spread out all everywhere, okay, across these several decades. Okay. All right, so this take-home message is that extreme sea level event, global anthropogenic global sea level rise, intensify the extreme sea level magnitude, but the preference of this extreme sea level events that for this 8-year period results from two effects. One, global sea level rise intensified, right? The other one, internal decadal climate variability also contribute about 0.1 meter. Okay, so these two together really explain why in the past decade, basically starting from 2010 to 2017, that's the most extreme sea level event occur in this decade because of these two factors. Okay, and so how the decadal variability intensify in that decade, intensified sea level along the Indonesian coast during that decade. So here I show the sea level anomaly, which is color, and the wind anomaly averaged during that decade. Let me hide that floating bar. Okay, all right. So here, and we explained earlier, this westerly wind really pile up water to the eastern boundary, and when they impinge onto this Sumatra coast, and the signal can also propagate poleward. Meanwhile, look at this, a longshore wind. This longshore wind, if we recall, and causes the ocean surface water to 90 degrees to flow 90 degrees to the left. Okay, so that convert to the coast. Okay, so you convert or push all the warm water to the coastal area, you increase sea level. Okay, so those both the local longshore wind and equatorial wind contribute to this increased sea level during that decade, which boost up the frequency of the extreme sea level event together with global sea level rise. Okay, and here we focus on the Indian Ocean, and as we know, from 2003 to 2012, that's we have intensified the Indonesian throughflow from the Pacific to the Indian Ocean. So we call this global surface warming hiatus period. We'll discuss next. So this may also contribute a little bit and bring the sea level a little bit higher from 2003 to 2012, although this only cover a little edge of this period. All right, for individual sea level extreme event, I do not want to discuss too much, but this one I show the surface wind pattern associated with individual, okay, extreme sea level event. This one also co-occur with marine heat waves. This one only extreme sea level, as we can see, it's strong equatorial wind and the longshore wind at the cause for this extreme sea level, even at interannual time scale. Okay, and this one only local wind play more important role. But for here, I do not discuss the details, but here we have a manuscript. If anyone want to discuss further, you can always reach me after the talk. Okay. So we just mentioned that there is a global surface warming hiatus period, okay, from 2003 to 2012. What is this hiatus period? So we showed in the first slide as we introduced, because greenhouse gas, increased greenhouse gas concentration in the Earth's atmosphere trapped heat. Okay, so it increased the sea surface temperature and warmed the ocean. So this is the time series of global surface temperature, including surface air temperature and sea surface temperature. Okay, starting from 1970s, as we see going up. Okay, warming, as we see this Earth's surface warming. But if we look at this decade from 2003 to 2012, almost flat. Okay, so here, and this surface, global surface, did not show the warming. It seems like stopped. That's why I call it hiatus. Okay, it's hiatus flat, getting flat here. It didn't increase. But if we look at the global mean sea level, continuous increase and accelerated increase sea level. Okay, here. So as we know, this is only surface temperature, ocean surface. Okay, but sea level, what does that sea level represent? The vertically integrated feature of the whole water column of the ocean. All right, so if we have the warm water converge in the water column, we increase sea level. Only sea surface temperature increase may not cause sea level increase, may or may not. Okay, so because this one represents the whole water column and this one only represents surface, and we know during the same period of time, greenhouse gas is still continue to trap heat in the Earth's climate system. Okay, so we still have excess heat in the climate system. And surface not warming, but sea level keeps increasing, and the sea level represents the whole water column. What does this mean? This means the excess heat increased is stored in the subsurface ocean. Okay, so increased subsurface ocean uptake is the major sink of this excess heat during this hiatus period. Okay, and for the same period of time, observations show dramatic heat increase over the small Indian Ocean instead of the big Atlantic and Pacific Ocean. And the amount of heat increase, okay, in the upper Indian Ocean accounts for almost 2/3 of this global ocean heat uptake. And where is this from? It's from increased intra-ocean circulation from the Pacific to the Indian Ocean through this Indonesian Throughflow, we call ITL. Right. So here, and to further demonstrate that, so here, as you see all those lines, and that's the average temperature at the surface and at different levels and until the 5,000 meters. Okay, global average is the black line. Global average at surface, as you can see, is negative, cooling if you average surface temperature over the globe. But the global average, the temperature in the subsurface from 100 meters to 400 meters is warming, further demonstrated that the heat is stored in the subsurface ocean. But if you look at the Atlantic, which is green, okay, it's cold upper ocean, okay, in deeper part of it, warm here, but a southern ocean, cold surface, and here subsurface ocean also show, okay, increased heat storage, but the maximum, Pacific show a little bit as well, the maximum dramatic increase of heat is over the Indian Ocean, okay, just like the previous study showed here. Okay, in the upper 700 meters, especially in the upper 400 meters, as we can see, right? So the right panel shows spatial, the pattern of the trend for this hiatus period in the upper 400 meters. Okay, temperature trend in the upper 400 meters represent ocean heat content in the upper 400 meters. And apparently, the heat is stored over the Indian Ocean, which account 2/3 of the global heat storage, primarily stored in the southeast Indian Ocean, although in the equator and here also have some. And this southeast Indian Ocean here, we store most of heat. There's a heat concentration in this area. Okay, because of this, and the temperature increase here, the 0.8 to 1.2 degree per decade, which is much higher than the global warming trend. Okay, and this pattern occurs in all the different ocean in-situ observational-based ocean temperature data set. Okay, and suggesting the robustness of this pattern. As we mentioned before, this if you have upper ocean heat increase in a specific area, it must be reflected by the sea level, because sea level represents a vertically integrated feature of heat, fresh water, and mass. Okay, so apparently that's the we have the high sea level here. Okay, strongest sea level rising trend in the Southeast Indian Ocean at 16 centimeter per decade, 16 millimeter per year, which is much higher than the global average sea level rise rate. All right, here we won't go to the further detail. This is a surface wind trend. We try to understand why there is increased through flow, increased heat and warm water transport from Pacific to the Indian Ocean, and why it's confined to the Southeast Indian Ocean. This is the sea surface wind. As we can see, the trend shows strong easterly trade wind, the intensified easterly trade I mentioned earlier. And this intensified easterly trade wind pile up water in the Western Pacific, enhance Indonesian throughflow, and is transported into the Indian Ocean. Okay, and after it entered the Indian Ocean, this clockwise wind pattern, as we see, confine this water to the southeast Indian Ocean. If we still recall, if the wind blows from the north to south in southern hemisphere, and the surface water we call the surface element transport is 90 degrees to the left. So it should be 90 degrees to the left when it should be onshore. So you accumulate the warm water onshore, you increase the sea level, increase the heat content in this area. Okay, so where is this intensified easterly trade wind from? They said this part of this internal climate variability called the negative phase of interdecadal Pacific oscillation. So here you do not need to know, you just need to know during this decade, you have intensified easterly wind due to the internal climate variability. And this internal climate variability redistribute the heat, okay, associated with greenhouse gas warming in the climate system. All right, to put this hiatus decade into longer term context, we show the upper 400-meter ocean heat content over the Indian Ocean blue and in the southeast Indian Ocean area. Okay, and here, apparently we see an upward trend. Overlying the upward trend, we have decadal or interdecadal variability, and there is intensified decadal variability in this hiatus period over both the whole Indian Ocean and the southeast Indian Ocean. Okay, so even though part of this upward trend might be due to anthropogenic warming and part due to internal variability, but this can be intensified by internal variability. Okay, so the ocean heat content during this hiatus period in the southeast Indian Ocean account for about 66% of the entire Indian Ocean heat content increase. And its area is only 24% of the Indian Ocean, suggesting that the southeast Indian Ocean off the West Australian coast has a strong heat increase, rapid heat increase in this area. Okay, so the rapid heat increase in ocean heat content off the Australian coast increased the frequency and the intensity of the marine heat waves. Okay, as suggested by existing studies that causes severe coral bleaching in the area. So this is the sea surface temperature plot as we see in 2010, and this is in 2011, which is a year of strong and prolonged marine heat wave. Okay, some research articles call this Ninglu Nino because Ninglu, that's the area, that's the location here, right off the Western Australian coast here. Okay, so that this is the difference between 2011 to 2010 sea surface temperature. As we can see, in some areas, sea surface temperature increased by almost 3 to 5 degrees. Look at it here. Okay. So this strong temperature increase and marine heat waves and intensified by the increased decadal scale ocean heat content have a large impact on the marine ecosystems. So this is the Ninglu Nino coast, which is very nice and has diversified marine species, and also its habitat to many marine species here. But during this marine heat waves, like we discussed 2011, the corals had bleached. Okay, so here they studied the two areas near the Ninglu Nino area, they call marine park, and two areas. Okay, that's one gray represent one region, the other like black represent another region, and just two study sites. Okay, only 2 kilometers apart, and they both at 2 to 5 meter depths. They measure this area, the cover area of coral, live coral, Okay. And so what we see, the 2010, that's pre-bleaching, the marine heat wave event. Look at this, cover almost this 57 or 58% area, and here cover 45%. But during this January 2011 marine heat waves, look at this, the live corals dramatically reduced, and here dramatically reduced. But a few months later, after the post, immediately after these heat waves, look at this black, the second area, it's almost zero, almost gone, all gone, okay? 8 months after this heat wave event, this black second area completely gone, like all the corals died, all right? And here only 1 to 60%, the first area, only 1 to 60% corals alive, okay? All right, so in summary, and the first part, we show a distinct regional pattern of multi-decadal sea level trend over the Indian Ocean. And this is due to the intensified atmospheric circulation. So the rising sea level trend in India and Bangladesh, Myanmar, and the Indonesian coast really increase their vulnerability to coastal inundation. Anthropogenic global sea level rise and high sea level anomalies due to internal decadal climate variability. And for the 8-year period, increased magnitude and frequency of extreme sea level event along this Indonesian coast, which increase the threat of the coastal flooding in this area, plus their sinking, the fast sinking of their lands. Lastly, the rapid increase of ocean heat content of the West Australian coast during this recent hiatus period and result from the enhanced intra-ocean circulation that's intensified Indonesian throughflow from the Pacific and the wind-driven ocean circulation that confined to the Southeast Indian Ocean. And the increased ocean heat content enhanced the intensity and the frequency of marine heat waves in the region, causing severe impact on marine ecosystems. Thank you. What's wrong?
Thank you very much.
Oh.
Thank you. I hope you could hear the clapping here in the room. Maybe you could not hear it, but there was a lot of clapping. Thank you very, very much. So we have a lot of questions already, I see in the chat. So I don't know if you can see the chat also yourself, but I will, in any case, I will read the question so that everybody also can hear it.
Right.
So we have a question from James Lord, and he writes, "Hi there, I'm not sure if you're taking questions via that chat. If they are, I would like to ask this one. Do these patterns in sea surface height anomalies persist throughout the year, or are they times of the year when the anomalies become more or less pronounced?"
Oh, that's an excellent question. Okay, very, very good question. We did do this. I showed here is the annual mean. And we did explore the southeast. We did explore because the Indian Ocean is subject to monsoon, seasonal, very seasonal. Okay, and the summertime and the winter time. And I think if I recall correctly, the winter time has a stronger inundation than the summertime season. That's the 2 monsoon season. Okay, that's an excellent question. Yeah.
There was a second question. Do we see similar patterns in the Atlantic and the Pacific as in the Indian Ocean?
Oh, that's another excellent question. And recently, I didn't bring that, but let's see this one. Okay, the first one. You look at that. And this is warming thing, the sea level pattern. I only looked at this. We are working on some US East Coast sea level. Okay, so in the past few decades, we there are extensive, I can't say extensive, but quite many research and discussing the rapid sea level rise along the US East Coast. And there are a lot of speculations. Climate model simulation show that if you have, we know Greenland ice sheet has been melting faster since the 1990s, right? And some people say, oh, because the Greenland ice sheet melting, you dump fresh water, reduce the Atlantic meridional or ocean circulation, you have a dramatic increase of US East Coast sea level. And some idealized model experiment using climate model did show that. But there's recent, I think 2016, there's high resolution model simulation work by Klaus Brunning. And he showed that the melting Greenland ice sheet water has not yet reached this US East Coast. This is still active area of research. By the way, if you look at this sea surface temperature warming, everywhere warms except for this south of Greenland, North and North Atlantic. And people use this as a strong indicator for weakening AMOC, Atlantic meridional ocean circulation, which might be a response to anthropogenic warming. Okay, all of these are active area research. In the Pacific Ocean here, my postdoc and we recently did the work. Like the Indian Ocean, if you can see overall warming faster than the central and the eastern tropical equatorial Pacific, because the warm Indian Ocean and cause atmosphere response, and you cause easterly trade wind in the Pacific Ocean. This easterly trade wind intensified cold water upwell to the surface, which they call thermostat mechanism, like counteract the surface warming a little bit. So maybe the Pacific, in the global warming sense, and warming is not uniform everywhere as well, maybe the warming in the ocean slow down the tropical equatorial Pacific cold town warming. But still, there might be some people disagree, but still active area of research. Okay. Excellent questions.
Thank you. There is a further question from Paul Temme, and he writes, thank you very much, Weiqing Han. My question is, does the ENSO circulation have an influence on the Indian flow through?
Oh, good, yes. ENSO does. Let's see, let's discuss this hiatus period. Let's look at, yes. ENSO, tropical Pacific Ocean circulation, the most dominant mode we all know is ENSO, yes. So when we have a La Nina phase, that's a negative phase of ENSO, we have intensified through flow, very clear. When we have a Nino phase, that's a warm phase of ENSO, and we have reduced through flow, the correlation is exceeding 0.8. I think is Gutenberg and Gordon, like Arnold's recent PhD student showed that part as well. Earlier work, I think Susan Rivers and Sprinto also showed the high correlation between the Indonesian through flow and the ENSO. Okay. And if we look at this hiatus period, and we show this, yeah, actually the intensified through flow and the surface wind, that's a negative phase of interdecadal Pacific oscillation. The interdecadal Pacific oscillation on decadal time scale. If we do the filter of Nino ENSO index, like an 8-year low pass filter, and calculate the IPO index and ENSO low pass filter index, the correlation is 0.89. So therefore, it's also under debate whether this decadal scale IPO mechanism, it's tied, linked to ENSO decadal variability, or they are independent climate mode. It's also under debate. Okay, thank you. I have here a comment from Graham Quarterly. He writes, England and Wang, or Klim 2015, suggest that ENSO has effect on ITF lagging by 8 to 9 months. And he's wondering if you would know some more references on this. Yeah, afterwards, if you send me an email, yes, I recently did do a lot because I recently, Arnold did, yeah, there is a lag, you're right. Yeah, there is a lag. And especially if you look at the Makassar Strait is 80%, almost 80% of the Indonesian through flow that enter the Indian Ocean. And Makassar Strait has a longer time series, I think 16 years, right? The instant, across here, like across here, they only have a few years, not continuous. But the Makassar Strait has the longest record. They also have a reconstructed. Maybe someone knows, like I'll find that reference. And if you email me or let me know your email address, I'll find it to you.
Okay, thank you very much. Thank you. Great. Then there was a question from Annie, and she says, what is the exact mechanism linking GHG and enhanced atmospheric circulation, hence stronger Earth easterliness in the IO?
Okay, so greenhouse gas. Okay, oh yeah, that's another good question. Let's look at it. I might have an additional slide put it here. No, I didn't. Okay, what does that mean? Let's look at this one. It will give us some hint. This one. See, this schematic shows the mean sea surface temperature pattern as you look at this color red. That's what we call the Indo-Pacific warm pool. Okay, and this cloud show atmospheric convection. That's the mean state. Okay, when we have greenhouse gas warming, all right, and as we show that pattern, and the Indian Ocean maybe you could hold warm, and the Pacific, as we mentioned, that assume we have uniform warming. To make things simple, we have uniform warming throughout this Indo-Pacific basin. And here, the mean sea surface temperature over the Indo-Pacific warm pool, that's the Eastern Indian Ocean, Western Pacific. You have mean SST exceeding 28 degrees and 29 degrees C. Atmospheric convection, as I show here, is very sensitive to the mean SST and the surface wind convergence, moisture convergence. So when the mean SST exceed 27.5, some people say 27, some people say 27.5, some people say 28. Okay, so when you have this, when the sea surface temperature exceeding a threshold, even a little bit change in the sea surface temperature, especially in the convergence zone. Okay, and it has dramatic increase in the convection, dramatic influence in the convection. Basically, it means that uniform warming added onto the mean SST pattern, it wouldn't produce a uniform convection or uniform wind. Okay, in the high warm pool area, you might intensify the convection, and this intensified convection drives surface wind change. Okay, that's a possible, that's a possibility. Okay, so if you have intensified convection, you have intensified the marker circulation, so you have intensified westerly wind. Okay, so that. Did I answer your question, Annie?
Maybe Annie will write back later. Let me maybe in the meantime tell you the next question. So this is Lei Wang, and he asks, a cooling trend occurred in the tropical Southeast Indian Ocean during 2003 to 2012. Is this due to weakened SEC or local Ekman pumping?
Which one is a cooling Southeast Indian Ocean?
Yes, and Annie writes that this was, thank you very much for the answering the question.
Is that showing here? Is that 2003? That's the Hiatus period. Talking about here, right?
I guess so. Yes.
Yeah, this one is actually consistent with our earlier work. Yeah, and here wind stress pattern, wind stress curve pattern. This one is if you look at the wind here, look at this red. These are Ekman pumping velocity. That's this guy. This one WE. And when the WE Ekman pumping velocity is positive, we suck up the cold water to the surface. We call surface divergence cause upwelling. So you would cause a cold temperature here, okay, because of upwelling. And you may say, oh, it should be in a central basin. We know this raspberry propagating westward. So you accumulate this toward west. So you may not see this the wind pattern, and this sea surface height or heat content pattern may be to the west a little bit compared to the surface wind WE at one pumping velocity pattern. Good question.
Thank you. Thank you very much. You have two more questions. So Tony Songreich's excellent talk. Thank you very much. You mentioned two mechanisms, WIND and ITF, for the IO warming. Do they enhance each other? So is there a link? Do they enhance somehow each other, or are they separate processes?
Oh, okay. Good seeing you, Tony. Thanks for being there. The intensified through flow is the source of this heat increase in the Indian Ocean. But where the water will store in the Indian Ocean determined critically by the Indian Ocean wind pattern. So this Indian Ocean, yeah. But regarding whether or not this surface wind pattern also intensified through flow, we didn't do experiment to examine that.
Okay. Thank you. And there is our last question by Ivan Orsoli. Is there a trend in the longitudinal Indian Ocean dipole associated with the intensified equatorial westerlies? Westerlies.
Oh, westerly wind. Oh, okay. Yeah, the recent work, oh no, you may be talking about this one. There are a debate regarding whether or not the equatorial Indian Ocean rock cell or even Pacific rock cell. We are saying the Pacific rock cell, right, it's weakening. And also, because of anthropogenic greenhouse gas forcing, the many research show, oh, we didn't see this in the observations or reanalysis data. Okay, and the Indian Ocean also, there's debate. They talk about intensified westerly wind. That's intensified rock circulation pattern showing in different reanalysis product. But climate models shows that the Indian Ocean dipole in a warming climate will be showing the intensified, like positive dipole pattern, which means the Eastern Indian Ocean, you have a colder SST, Western Indian Ocean, you have warmer SST. If you think about this atmosphere ocean coupling, you would have intensified easterly wind. But if you look at the wind product, it's very difficult to be these two. It is under debate, the wind product. We don't have a pretty long, reliable long wind. So we do have this reanalysis wind I analyzed recently for different reanalysis wind product. They converge in describing Indo-Pacific rock circulation. They converge starting from 1967 also, or starting from early 1970s to the end of 1960s. Earlier than that, they're everywhere. The reanalysis product, they do not converge, even for describing this Indian and the Pacific surface branch of the rock circulation.
Thank you. Maybe also a last question from my side. Now, we just had the climate conference, of course, in Glasgow, with the goal of reducing the global warming to maybe 1.5 degree. Did you do any calculation what such an increase would mean for Indonesia, for example, or for Western Australia? Do you also make projections for the future with the models?
In that area, regional projections, I don't know how reliable it is. And when I analyze the regional sea level patterns, and the climate model give us different answers. Each model gives different answers. So for future projection on this area, I'm not aware, I haven't done that, but we can look at whether there are consistent signals in these regions in the future under greenhouse gas warming. and from different climate models, whether or not they are consistent.
Okay.
Thanks.
Yes. Okay. Are there more questions in the room, maybe? No? Okay. And thank you very much for the talk.
Thank you.
This was great. And also a lot of questions. And so we will.
No, I enjoyed it. Thank you.
Thank you very much for joining us. Before we stop, let me make one last announcement about the next talk by Sabine Schindler. This will be on the 30th of March. And now the people here are invited to a small apéro outside. And with that, I would like to thank you everybody again and wish you a good evening or a good day. Thank you very much and bye-bye.
Thank you.
Thank you very much.
Thank you.